Hello everyone, my name is Konstantin Vladimirov. This is lecture 2 of our Master's C++ course. And last lecture we discussed what seemed like a very simple algorithm for finding the most significant bit of a number. I'd even call it a dumb simple one. But as it turned out, attempting to generalize it opened up a surprising depth and complexity. We also talked about program behavior, including undefined behavior. And today we will talk about another motivating example of generic programming, this type dealing with generic types. But we will start with a certain depth. Last time I didn't show you how to write Hello World in the C++ programming language. Pause the video now and try to write Hello World in the most modern C++ you know and make it work like on Godbolt. We are using C++ 23. I remember. 3, 2, 1. Okay, here it is. However, getting it to work is not so simple. Last year, this thing didn't work in any production compiler. And keep in mind, last year was 24, and language standard is 23. It didn't even work on Godbolt. Getting it to work on Godbolt still isn't easy. And let me show you the compiler explorer on this link. Okay, and now you see it. First, you need to have CMake-based Godbolt project. Do you know how to create CMake-based Godbolt projects? Now you know. Okay, in the CMake, you need this little incantation. I hope you know those numbers by heart. You need to have CMake 66 models on, and you have some target sources and CMake 66 standard. And here you need to specify Ninja generator. If you are not specifying Ninja generator here, nothing will work. And here you need to specify std_lib equals libc++. And if you don't do it, nothing will work. And here you may enjoy that your standard library just modularized and this application built and collate worked fine. And after such warnings of CMake, you can see Hello World. Great. This is about this import stud. And this is like unexpectedly hard for Hello World. In the language, after 2 years of this is official Hello World. And we will have a special lecture on models where we'll figure out why this was so difficult, why it took so long to get here, and why you should make your projects as model as possible as soon as possible. For now, it's optional. For now, Hello World in modern C++ just working fine. Of course, we may do it simpler. Hello, simplify world. Of course, we can simplify this a bit to make it slightly easier to get working, and minimal simplification is hash include print. Actually, for those who watched the latest ZeroCost in Russian, it's already on YouTube. Paluchin's talk about modularizing Boost. They essentially do this. They create includes in Boost, and then under various compilation conditions, they introduce imports into this includes. Or we can use the very classic C++, C++98 with to cell. Or if you want to use more classic C++, but still have cool formatting capabilities, what can we do? Okay, we can use hash include format. And hash include format is a good old libfmt library that was standardized, and the header is called format, and we can use formats almost the same way. Or how else can we write Hello World? Use the good old API from the C language. Okay, this was 5 ways There were 5 ways to write hello world, each better than the last. Actually, there are more, but I'll stop going down this path. Otherwise, we'll get into write, puts, and so on. Okay, and what do all these hello worlds have in common? We've come a long way from 1983, I believe this is 1983, to 2025. But something has remained exactly the same in all those code snippets. Pause the video and take a moment to look at all these options. What do they all have in common? 3, 2, 1. Of course, this is the string hello world. The string hello world is the common thread. They all use the exact same identical looking string literal. But what does that mean? What is a string really? And how is it possible that a string literal from 1972 from C language looks exactly the same in 2025 and just works? So, what is a string? Imagine you have some function foo and you want to pass here a string literal. And how do we encode it? For example, we could have this idea. We encode the size first and then the string. The size here is 14. Oh, looks like I'm mistaken. It is 13. Okay, okay. But let's say I can make an error in this size. Yes. Uh, what's the problem with this encoding? And there is a simple reason of problem. What type, may I ask, will this string have when passed to a function? If it's encoded like this, what's its type? And you would have to do something magical. Some magical compiler built-in type for strings, define their interaction with other types in the language, and so on, so on. And so, quite a long time ago, even before the C language, people came up with a truly brilliant solution: null-terminated strings. Null-terminated strings solve this problem. Now this literal can be converted to a const char pointer, and we are done. And so null-terminated strings won over everyone. Notice a very beautiful feature. Any pointer inside this string is also a string. And as soon as you find the null character, that's the logical but not physical end of the string. Does anyone know how startalk function works in C? I want to take a nice string, say by commas, and this function will insert a 0 after each comma and tokenize this string. And you might stumble upon 0, which for print signifies the end of the string. But you can skip it and go further because you know where the real end of the string is. A genius solution. Genius. Also note, this literal is converted to const char pointer, and the size of the literal is 14, and the size of pointer is 8, and you can see it in the output. And when you use the literal, it behaves like a pointer. It is implicitly converted to a pointer. And of course, in the C language, we know how to work with char pointers. And despite the sheer genius of this solution, we are going to spend the rest of the lecture picking it apart. Okay, let's start with how are we working with C strings. I already told you about this startalk function. Here the functions are listed in the order of surprise. Star CPI, okay, our favorite method to copy. Strcut, maybe I used it a couple of times. Strcmp dude, better not. Strchar, oh, that was in second year, even if you are 50 now. And the standard library is very rich of capabilities. But there is a small problem. Using strcpy is really dangerous. Why? Of course, the input is not a null-terminated string. This function will just keep copying, causing all kinds of bad behavior in this world. And this is unsafe, so security specialists made a safe libc for us. What could possibly go wrong? Yes. Let's consider std strncpy. I don't know how to spell it, sorry. Why doesn't this work? What is problem with strncpy, which takes the size n? First, idea itself is cool. We say we copy no more than n elements. Of course, there are questions. Does this n include terminating null? If we reach n and haven't found the terminating null, do we insert it at the nth or n plus 1th position? And let's say you read that in the documentation. But there are more substantial problems. The first question, which function can we not improve like this? And that, of course, is strlen. What is strn len? Search up to n and then give up? But even if we improved string copying like this, did security get better? No, it didn't. Let me show you my favorite XKCD comic. Serever, say potato, 6 letters. Potato. You see, this is a strncpy in its essence. Say potato, 6 letters. We are specifying the string and a number of letters. But there is something else written here in gray font. Server, say bird, 4 letters. Again, gray font reveals some secrets. But the server says bird, all good. And now, server, say hat. 500 letters. Answer, hat. Lucas is looking for missed connection page. Administrator wants to change the server password to this one and so on. This is called Heartbleed. You can read its wiki page. The Heartbleed vulnerability existed from introduction to its fix in Linux for 2 years, during which you could exploit this server to the max. And how long was it there before discovery? And so, what is the problem with C strings? What is the main problem which allows such strange and truly scary things to be done with them? Many millions of dollars, gigabytes of databases, and so on were stolen purely because of C strings. And people who promote trust, why do they promote it with such persistence worthy of a better cause? Because it is indeed a scary world. The world built on the C language is scary and we have no other. The whole world is built on the C language and it is scary. And the main problem of C strings, length is not string invariant. We would like string to maintain certain invariants. One of these invariants is its length. Actually, we would like the string to maintain other invariants. For example, if it's allocated in dynamic memory, there the pointer to its beginning is indeed a pointer to the block you allocated from. So you don't do delete on pointer plus 4, etc. And if you want to preserve invariants, how can we do it? And I believe you know that to preserve invariants, we need object-oriented programming. Or rather, not exactly. Object-oriented programming is needed to preserve invariants. This is the main motivation for opaque principle. To preserve object invariants, we need encapsulation. We need private state which is inaccessible for modification by anyone except the methods of the class itself. And this leads us to the wonderful idea of writing our own string class. Shall we write it? Shall we? If you said yes, congratulations. This creative challenge is for you. Draw me a bicycle and let's see if you can reinvent the wheel. To make good bicycle, you will need to invent at least two wheels, right? The slide lists strings that exist in the wild right now, and I'm only listing those actively used. This is really millions of lines of code with this string, with each of the string. C string from MVC, Q string from Qtil, C com bstr from IATL, a string from Facebook. The whole Facebook lives on its own string. Moreover, this string was designed for them personally by Andrei Alexandrescu, if you know him. I will have a talk about this string in the literature list in the bibliography. G string from GTK. All GTK lives on its own unique strings in C, by the way, with macros and void pointers. And finally, for 3D graphics, EISTL string, supposedly optimized for graphic application. Very cool. Also, millions of lines. And since we're unlikely to do better right away than all these worthy people have already done, let's study some string. Which string do we want to study, considering that this course is about generic programming in C++? Of course, std_string. And let's see how std_string is structured in principle. Look at the picture. The string guarantees memory continuity and reallocates if needed. So it has size and capacity fields. Capacity is always more or equal to size plus 1. And this picture lies, but we'll find out how later. As a principal scheme, it's good. And what is fundamentally strangest thing here? How do you think? 3, 2, 1. And I think the strangest thing here is the very presence of the terminating null. Why do we need a terminating null at all if we already store the size? We already spent on the size, but sort of decided like to take the best of both worlds and also kept the terminating null. For what purposes? And of course, I hope you guess for what purposes. This exists for backward compatibility. We have two methods, one scarier than the other. I hope you never call this one with data, because through this method you can even modify this string a bit. But to pass a std_string to a legacy C API, you can call C str, and you can get a constant pointer to the string and pass it wherever you need. But this is really convenient. Let me summarize. Std_string, everything we see is a net word. First, automatic memory management. We assign std_string s equals hello. Memory is allocated immediately, and importantly, the string owns that memory. It will be freed when the string goes out of scope. Next, size is an invariant of string, and generally many things are string invariants. Next, we have string literals. The literal hello followed by s is a std_string starting from C++20. Everyone understands why sz equals 2. I hope everyone understands, because it's the string method find first of that finds the first of the letters in KLMN string in the word hello. And next, compatibility with legacy C API. All legacy functions you have if you really want to use them, will continue to work even though they are unsafe. Just pass your string here and refactor later. Perfect. C++ is an increment on C. C++ toString is an increment on C string. Did I sell you the strings? Yes, did I sell you on strings? Will you always use them now? And are there any clouds on the horizon? And here, we are programmers, yes. Here I expect some skepticism. Pause the video and try to formulate something skeptical. 3, 2, 1. Okay, first skeptical bullet from me. The first thing I want to emphasize is dynamic memory allocation. But besides that, it's allocation in unexpected places. Because let's say I want to declare this and then call foo and question, is this a good idea? Try to criticize it. And for me, the worst here is memory allocation before the main. And this is heap interaction before the main. And what if we get a real beta log exception before main? How will we ever handle it? Have you ever caught an exception before main? How you do it in your program? Moreover, this is monstrous initializing code if you look at it in Godbolt Explorer. Let me show you. This one. Okay, this one is toString, and this one is calling foo, and this just to not optimize things away. And what do we see? We see rather reasonable main, but here to do this, we do see this, and this is real nightmare. Oh, compiler even vectorized it for you. So sweet. And of course, because exception is unhandled, it calls abort. It calls abort. Do you like abort for main? I personally don't. Okay. Um, can we do something with this? And I have one idea. I have one brilliant idea. Replace it with a pointer. Of course, the string is already here. Let me show you again. The string itself is already here as .ASCII-Z. It is, in some sense, a pointer. It is an address in your, raw data section, I believe. Why not to have it just a char pointer? Is it a good idea? Pause the video for a moment, and of course, it became worse. Because now all this machinery, do you think we removed it? No. We moved it to the call side. Now foo with argument s must do all this every time. Let me show you. This is how it was. It was awful. And this is how it becomes. I think it becomes worse. Because now it is on call side inside main, where we called foo. We need to make all this heap dereference, initialize everything, and even vectorized operations not helping much. Okay, therefore, we don't want to make foo take a char pointer. Why? Because if we do, we will return to the scary C world. Server, say head, 500 symbols. So we do not want char pointer here. And what is solution? And So I will sell you the solution, string view. What constant is, we'll talk later, but you can guess it means we guarantee that initialization happens at compile time. No additional things will be generated here. Here, string view is a non-owning pointer, and it is a pointer that does not own what it points to. In assembly, it would look something like just pointer assignment or pointer passing to function. Please click on this link to investigate how will it look. And because before we had a const string reference and the string itself is a pointer and reference is a pointer, that's two dereferences. Now we do have one dereference, and now it's clear. And how string view is structured in principle? Essentially, string view is structured as shown. This is the same lie on the previous picture, but it's also not fundamental. You have someone who owns the memory, like string owns the memory. And you have someone with string view who encapsulates its size and a pointer to what someone else owns. And let's give a string view a try. String view have very interesting interface. Its non-allowing nature is perfect because, for example, computing substr in a regular string is quite expensive. Why? Because you have to allocate new memory in this case. Computing substring in string view is very cheap. It's just two pointer operations, and this will all fold into fairly cheap computations. So we do have string and we do have string view, and everything is great, right? Cool. Happy for you. But there is a problem. Pause the video and try to identify where the problems might be. Here, 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 or here. And of course, 3, 2, 1, solution is here. This is a string no more. For those who don't know, there's Monty Python sketch where they discuss a dead parrot. The seller constantly denies that the parrot is dead and moreover nailed to the perch, while the buyer constantly finds new synonyms to express the thought that the parrot is indeed dead. And so we are used to different dead parrots. We understand that a pointer can be pointer no more, that a reference can be reference that expired and gone. But what do we not anticipate is a value to be an X value. And the main problem with classes like string view is that this dangling is hard to notice if you're not specifically looking for it. The value here is not annotated, and it can dangle. Okay. Value semantics are needed precisely so that nothing dangles, but here we have value that dangles, and this is a problem. And let me show you one more dead parrot example. Another example, it's clear that the second line won't work. Of course, this won't work, but will the first one even work? Pause and try to answer for both cases. 3, 2, 1. Of course, this is okay. And this parrot ceased to be after the full expression. The second with dangle. And what is correct use of reference types? We may give some guidelines like only temporary values, they should not be stored and so on. But in C++ there are no guidelines. You see, you may use those type as you want, but what I want to give is not a guideline, it is a rule of thumb. So, the rule of thumb is only use these types, like string view-like types. We will see a lot of string view-like types in the lectures to come. So, only use these types in two places. First, in function parameters. Why? Because the owner is on the outside. The caller owns the memory, so you're safe inside the function. Here, okay, everything is great. You are safe here. Whatever I do, it will not tamper because someone else owns this memory from outside. Second, in for loop initializers, like in this example, we have a vector of strings and we iterate over them as string views. Great idea and completely safe. If you see them anywhere else, that's a huge red flag. You need to stop and double check the lifetimes. Okay, do you see any other problems? Look at this code. Pause the video. In what cases can string be less efficient than C-style strings? 3, 2, 1. Okay, the problem is, of course, memory allocations. I highlighted these lines in red. Memory allocations happens in them, or might happen in them. And to demonstrate you that memory allocations are tricky thing, allocations, tree allocations, let me show you the examples of forming strings. Of course, in the language where we do have 5 ways to write hello world, we have several ways to concatenate some strings. And what do we do? We have some string path, some string query, and some string protocol. The protocol, which can be either HTTPS or HTTP. And then the path, and then the query. And we can do it in 3 variants. First variant, we can simply concatenate them using the plus operator. Second way, we can use input-output streams, like this one. And third way, we can use this stud format and pass things to it and get a stud string as an output. And stud format have great advantage. It is like locale independent. Locale is optional for stud format, and locale is mandatory for string. Okay. And I have a benchmark. Pause the video now. Which of these methods do you think will be better? And of course, you anticipate the better one will be newer, will be this stud format. Okay? Let me show you the benchmark. I'm using quick bench by the way. Okay, this is the benchmark. This is string, this is query, this is how we form a string, this is plus operator, this is your streams, this is stud forward, everything is fair. And as we can see, the I streams are slowest one, stud format is 1.7 times better, but direct sum is 4 times better. It's huge. It's like so the most obvious, the most simple way wins here. But wait, do you see some problem in this benchmark? And I do see, because what are we benchmarking? We are benchmarking everything inside this for loop. This for loop and this for loop. And inside this for loop, we do have 2 constructor called, not one, because we are also constructing this string stream. And every time you see some benchmark in the internet, in some videos on conference, please always anticipate that someone wants you to believe in some false statement using this benchmark. Can we fix this benchmark and fix like strips? Okay, we can. Sure, we can. Instead of measuring the construction of string stream, we can construct string once and then measure the rdboof pubseq pos function that just unwinds the stream to the beginning, rewinds stream to the beginning. And you, of course, want to see this code in your code base, okay? But it is fair now. Now we are constructing only one thing, and this one thing is resulting string. Let me show you the benchmark now. And the benchmark now is like this. Stud format happened to be the slowest of all. And did you remember what I said like a minute ago? If someone shows you benchmark, he wants to derail you. In this case, this is me. Sir, please look into what I'm benchmarking, how I'm benchmarking, and try to make this benchmarking reversed. Like, try to make fair looking benchmark like this, where stud format will be the fastest and direct sum will be the slowest. It is interesting, really interesting task. Okay. By the way, stud format have a really interesting structure. It's a very interesting header because it have this stud format string in it, and stud format string wraps stud string view, providing a compile time constructor for it. And therefore, the format string can be recognized very efficiently at compile time and checked against the types. But I have one more problem with when I'm working with strings in the style of the new print and format, and it's not a problem for you because I believe you are all young and hot, but it's a problem for me, and that I have to learn format strings again. And I struggled with print back when I was 18, honestly. When I learned all those %+z or PRIU64, I had enough of that in my life. And now they offer me to eat these too. Intuition check. Try to say what will be on the screen without trying it in your console. If j is 0, I is 42, and this is also j, so this is also 0. What will be on the screen here? What will be here? What will be here? And what will be here? And this one is hardest one. And then try to check how are you understanding those smiles. For me, it's nightmare, but you might feel differently. Okay, and let's talk a bit more about performance. Suppose your program has many identical strings simultaneously. You have S1, you passed it somewhere there, it's copied it somewhere else and passed the copy somewhere else and so on and so forth. And you have 4 copies of is S1, each owning memory, each wasting memory. What to do? Okay, we can do it like Java. We can have copy and write. We take and introduce this ref count in the string buffer, and our string is now just pointer to the string buffer. the principal scheme is correct. In reality, this will look different. I don't like interf count because buffer is probably a global shared resource, so it should be atomic. And this is called copy on write. Why? Because if you have this string s1 equals to hello and this string s2 equals to s1, then s2 just shallow copy it to have a reference to the same string buff with increased ref count. So this string buff knows that there are two string references it. And if we are modifying one of the strings, like this one, we can unshare the buffer and reference counters are back to 1. How will it be implemented in real compiler, in real library? Let me show you how it was implemented in libstd++ version less than 5. The control block lived here, very convenient, and here was the string itself. And notice, by the way, how cool it is that we have a null-terminated string, and here, before the string, we are storing everything else. Cool, right? Genius solution. But from the very beginning, cows was very actively used. According to most measurements, saved a lot of machine time and memory space. But cow strings always had opponents for some reason. And there are still supporters of cow and opponents. And for example, the advantages of cow include memory savings. And try to pause video now and try to guess what are advantages and what are disadvantages of cow strings. And how do you think what is the balance? Are advantages or disadvantages win? 3, 2, 1. Okay. Let me list you someone. Advantages: memory savings, cheap copying, fewer allocations and deletions in the heap. This is performance gain because allocations and deletions are expensive. Disadvantages: extra level of interaction. The copy operations virally spreads into all modifying operations. And this one, multi-thread cow disease. What am I mean? Because if you are using cow strings in a multi-threaded environment, if there are thousands of threads, atomics inside ref counted blocks will serialize on those threads. And in the second part of this course, we will look at how this happen. We will look at how to handle atomics in such ways. And this is really nasty for heavy multi-threaded programs. But there is a consideration that breaks a balance because overall it's a balance. On the other hand, cheap copies, on the other hand, fuel allocations and cache hits, then the blue and the red on this slide are the balance. If it were only this, cow strings would have remained in the standard with their pros and cons. But there was a consideration that broke the balance, which by the way is not listed here. And it is really not obvious. It was well understood many years after the strings were invented, and this consideration is pointer invalidation. Pointer invalidation happens, and that's normal. We are used to pointer invalidation. Okay, it's like regular dead parrot case. Okay, so we have string hello. We took const char pointer p. We amending this string with a word, and now this p is parrot no more because it may dangle. Memory may reallocate. And if reallocation occur, then because the string guarantees memory continuity, probably memory was allocated in some other place, and this pair is now pointing to nowhere. And here there is no problem. We are accustomed to pointer dangling in such cases. The problem is that cow string pointers are invalidated by seemingly harmless operations. Admit it, you don't expect memory allocation for a string when you just write a different character to one position. But it shares the buffer. We do have this string S and some buffer for it. We have pointer inside this buffer. Next we have S2 sharing buffer with S, and then we're unsharing S buffer, and P is now pointing to nowhere because S2 lifetime ends here. And now P is dangling. And this cannot happen. This cannot happen with regular non-cow string. We changed one character in the string, and your pointer inside the string was invalidated. This is unexpected and unpleasant. And in 2011, I believe, the standard was changed so that strings could not invalidate pointer when executing the subscript operator. So now the official requirement for the string in containers, the string must not invalidate pointers during subscript operator, and this requirement killed cow. Because a cow string in the subscript operator, if it was shared, had to do an unshare, and unshare is allocation, so on and so forth. Therefore, cow strings were practically forbidden with this new limitation by the standard. So cow is almost dead. But in reality, cow strings are useful, so a lot of non-standard solutions exist. On this bicycle, there are more than one cow, including really widespread solutions like aforementioned Q-string from Qt. It is still cow, okay, but can't we really do anything at the class design stage except cow? And yes, we can. Yes, we can. Let's return to the picture. Let's go back to it. And I'll now tell you where I lied. And actually, I lied about the scale of the picture. Look how small the size field, how small the data pointer is. And what is actual size? Here it is. I redrew it to scale. This is the actual scale. Here is your control block. This is data. This is size. This is capacity. And this is the string. And of course, when you're looking at this picture, you understand. If the string is small, what can we do with it? Put it in the control block. This is called small string optimization, SSO. The slide shows the worst possible way to implement SSO. We combine some fields of the string with the data for the small string as a union, which is bad idea for C++. And can you find any problems with proposed solution? 3, 2, 1. Yes, there are some problems. On every read, we add time for a choice with a size check. The most frequent average operation of strings is reading from string something. And we are paying now for every read. We must decide where we're going, in the memory, or in the heap, or inside the string itself. And also all these things are also nasty, but nothing compared to this. can we somehow deal with it? And yes, of course. In GCC, in libs2c++ version greater or equal than 5, the string looks like this from C++11. We losing data and size, but except of capacity, we also adding some padding to have 16 bytes for small string optimizations. And data may point to heap if there are capacity and padding, or point to small string if there is a size. We can make a dangerous assumption. If the string is small, why store the size in the full field? And this leads us to Alexandrescu's design of a string. And you can look at other ideas how to make efficient SSO, but in libs2c++, this option is implemented, and it is quite good because the same pointer points either to the place for small string or to the heap. And we will have a room to 16 characters. Will we have a room for 16 characters? Oh no, we will have a room for 16 bytes because there is another problem here. There are different types of characters and different types of strings. UTF-8, UTF-16, UTF-32. You could write 3 different string classes for each type, but the string class has many methods. 98, I believe. Like 89, I believe, public methods. And in the opinion of Herbst, like 69 methods are unnecessary. And rewriting every method is not desirable, so it's better to use class templates. Okay, we invented generic types here. This is of course not how real basic string looks like. This is a lie. Please wait for next slides for real basic string scheme. Okay, so we want to make a template basic string from char t with the pointer, data, size, capacity, small string optimizations, and every good stuff like this. And for convenience, just for convenience, we want to define some aliases like string, u16 string, u32 string, w string, and we have small problem here, really small problem, because if we do have like 89 methods, suppose inside one of those methods we want to understand if a character of type char t is the end of file. How do we do this? You see, we do have char t, we have some methods, and one of those methods may want to like compare if char cycle, make it lowercase, test it for end of file, and so on, so on, so on. And this is not simple, but we do have a good idea by using here type traits. There are two options. Make the traits alongside so the string doesn't know about them. This is sometimes done in locales, or make the traits part of the string type itself. If you make the traits alongside, you lose the ability to substitute any custom implementation for char t. If you pass the traits as part of the string type, then for a regular char, you can use not even stu_char traits, but anything. And this is an important engineering decision to make traits part of the string type. The traits contain methods listed here, and everything done in basic string is now done through traits. For example, for comparison, traits like traits called COW and SSO is code. and how will we allocate strings? Is the memory allocation method per character a trait of the character? The alloc method doesn't say how much to allocate. It says where to get the allocator from. We will have the full separate lecture on allocators, and 2 lectures. And I will tell you everything about allocators. But for now, just remember, allocate is not a trait of char. Allocate is a facility for container, for a container. No. Like in the string, control block needs to be allocated. In the list, the whole structure wrapping the pointer shall be allocated. So, okay, and therefore, basic string, and this is the real basic string. Basic string has 3 template parameters: char t, traits, and allocator. Traits have default stud char traits, and allocator have default stud allocator. Everything is done through traits and through the allocator here. We are not calling row new in the basic string. Okay, and you can use not only characters in the string. For example, you could pass traits for float and make a basic string of float. That's already an exotic case, but let's consider some strange example. We do have some function toggle that have a sequence of bool bits on the entry and toggle each other. Toggle each of them, like toggle each bit. The compiler complains. The compiler here cannot bind non-constant reference because vector bool proxy references are error values. What to do? An interesting option is to use stud basic string instead, because basic string bool stores bool, the real bool objects, unlike vector bool, which often uses bit packing. Furthermore, basic string provides continuity guarantees, unlike deck bool. But this is of course a joke. I believe you understand that you will not do like this. What will you do? Okay, you will use std_span. Actually, in the toggle function, it's better to use std_span. Like this. Std_span is an analog of std_string view, but for anything. It's a non-owning view with value semantics, and a good view that can be passed and used is std_ref view, but we will have, you guess, separate lecture. When more about views will be covered in great detail. And std_span is sometimes called a bad view because it raises information about whose view it is. Like here, it doesn't know if it's view of vector or an array, but for its purposes, it's good. We can make a basic string of boolean main, pass it to toggle, and basic string happily converts to std_span. A vector also converts to std_span. Anything that can be iterated linearly converts to std_span. And now we can say that you are ready to reinvent the wheel. Because now you know a lot about string classes, and you may be ready to write your own one. Okay, homework assignment. First homework assignment worth 3 points. Write your own great cow string template class. I will subjectively measure the greatness. Homework 2. Write template class string twine. I'm compiler engineer, and in the LLVM compiler infrastructure there is a twine class, which is great. And I want your twine class to be even greater because I expect your twine class to be based on the raw data structure and to spend no more than log from n iterations concatenating the several string views. And third task is even more interesting. The deadline for every task is 1 month. Third task, compilers now strange optimizing string. Let me show you. This example, thanks to Belov for this example. We have some function foo, and we have const vector, and const vector is optimized perfectly. When I look at this code, I may say C++ is my favorite garbage collected language. It collected like everything. But here we do have a bar function and the same pattern to think. And it is not optimized at all. It is like calling delete, no garbage collection. Why? And I expect you to dig into it, like if you can understand why is it happening and create a little reproduction to show me, maybe in comments. It is like 2 points. If you will have a patch to any industrial compiler to fix it, this is perfect 10 for the course. Okay, I really value your contributions to industrial compilers, as you may know it already, and some bibliography. Okay, first 2 bullets you understand. This is language standard, and this always will be here. I really recommend this talk, Nicholas Ormond, The Strange Details of String at Facebook. This was Andrei Alexandrescu who designed Facebook string, and this in Russian. If you know Russian, Anton Paluchin, how don't do. I may. It is really hard to translate the name of this talk. It's highly idiomatic in Russian. I really suggest that you will see this like lightning talk of John Don Mueller. C++ string literals have the wrong type. CPP on C. This talk is great, and all other talks in this list about string views, about format library, and so on. If this lecture was very short for you, you may spend another 5 hours only in my recommended playlist for this lecture. And we touched a bit in generic programming, and we are lacking something. We want more generic programming because we have only one building block for generic programming, and one building block we invented today is generic class. But generic classes themselves are not enough. We need a second building block, and this second building block is not a generic function as you may think. The second building block is the overload set of generic functions. In the next lecture, we will concentrate on overload sets of generic functions. And that's all for today. Thanks for everyone.